So in the first video, we talked about graphing systems of equations and using the graph to find the solution for the system of equations. In this video, we're going to talk about a different method to solve a system of equations that will help you find the exact solution without using a graph. Now you probably wondered in the first video how I knew this point, 2, -1, was the solution for this system of equations. Now I could have graphed both of these equations and I could have seen that they crossed at this point, they intersected at this point, 2, -1, making it the solution for the system. Okay, so that graphing method was the one we did in the first video to find a solution. Now I'm going to show you a way that we can solve a system of equations such as this to find the exact solution without having to draw a graph. So the method that we're going to talk about is called substitution. Now substitution is just a method for solving systems of equations that involves the substitution property of equality. That's a property that we use all the time and that we've talked about before, closer to the beginning of this class. So let's define substitution as a method for solving systems of equations that involves using the substitution property of equality. Now the substitution property of equality tells us that we can substitute in values that are equal for each other. So if we have two things that are equal, we can substitute them in one for the other or vice versa in an equation. So let's say that we knew the equation 2 plus a was equal to 7, and we knew that a was equal to 5. We could substitute in the 5 for the a and still get a true statement. So that's using the substitution property of equality. If we know two quantities are equal, we can substitute in one for the other. Now there are lots of ways to use substitution, lots of choices you have to make while solving a system of equations. I'm going to show you the way I do it first, because it involves just using slope-intercept form. Now if you're ever unsure of what to do when solving a system of equations, it's always a safe bet to put it in slope-intercept form because you'll be able to tell if the equations are parallel, if they are the same line, or if they are different lines. And if they're different lines, I'm going to show you how to find the exact solution. So let's take a look at the first example. Now, both of these equations in our system are already in slope-intercept form. And we can see that they're not parallel since their slopes are not the same, and they're not the same line. So we know it's going to have one solution. So this is how we're going to use substitution to find that one solution. Now we know that our y is equal to this expression, and we know y is equal to this expression. So we know the expressions are equal to each other. Since a number is always equal to itself, y is always equal to y. So we can substitute in our first expression for the first y and our second expression for the second y, or simply set the expressions equal to each other. So we have 3x plus 1 equals the opposite of x minus 7. Now we have a single variable equation. We know how to solve this, so let's go ahead and solve it for x. So we find that x is equal to -2. So this means our x-coordinate is going to be -2. This is our x-coordinate. So in a coordinate pair, we have an x-coordinate and a y-coordinate. So if our x-coordinate is -2, we need to find our y-coordinate. Now we could substitute what we found for x, our value for x, back into either one of these equations to find our y-coordinate. Now it doesn't matter which equation you choose because at that solution point, the x-coordinates in both equations are equal and the y-coordinates in both equations are equal because it's a shared point. So let's take our x equals -2 and let's plug it back into our first equation. We're going to substitute it in for the x since we know it's equal to -2. So from our first equation, y equals 3 times, well, our x is -2 plus 1. So y is equal to, let's simplify, 3 times -2, -6 plus 1. So y is equal to -5. So our y-coordinate is -5. So our solution point will look like -2, -5. So to double check, you could put that point back into each of the equations. Simplify it. If you get a true statement on both, you know that that point is a solution for both equations, and if it's a solution for both, it's a solution for the system. Now, if you'd like, we can show that we could plug our x-coordinate back into the second equation and we would still get the same answer. So let's just go ahead and verify that. So putting our x-coordinate back into our second equation, we have y equals the opposite of, and our x is -2, -7. Opposite of -2 is 2. So simplifying, y is equal to -5. We still get the same y-coordinate. So that shows that you can choose either equation when you're substituting back in your x-coordinate. You can use either equation to find your y-coordinate. Now you don't have to use both. That step was just extra just to show you that they both work. So it's up to you which equation you'd like to use. I always go for the simpler one just to save time. All right, let's go ahead and look at the next example. Now one of our, actually neither of our equations are in slope-intercept form. So let's go ahead and put them in slope-intercept form. So here's our first equation. So our slope-intercept form, we want to get that y by itself. Remember, y equals mx plus b. That y is isolated. We have our slope, our x-coordinate, and our y-intercept. So let's add 2x on both sides. We end up with y equals 2x plus 1. So there's our first equation. So in slope-intercept form, our first equation looks like y equals 2x plus 1. And let's try our second equation and put it into slope-intercept form. So we're starting with y plus 2 equals 4x. Just subtract 2 on both sides. So we get y equals 4x minus 2. So our second equation in slope-intercept form is y equals 4x minus 2. Now we can see that they are not parallel since their slopes are not the same, and we can see that they're not the same line. So let's go ahead and do our substitution. Since we know these lines are different, they will have one solution. So let's find that coordinate where their solution is. All right, so we know that y is equal to this expression and y is equal to this expression. So the expressions must be equal to each other since a number is always equal to itself. Since y is always equal to y, we know that this expression, since it's equal to y, and this expression, since it's equal to y, will be equal to each other. So let's set them equal to each other. Now it's a single variable equation. We know how to solve this. Let's take 2x from both sides. Let's add our 2 on both sides. Divide through by 2. We end up with 3/2 equals x. So our x-coordinate is going to be 3/2. Now all we have to do is take our x-coordinate, 3/2, and plug it back into either equation because we need to find our y-coordinate. So like I showed you in the last example, either equation is going to work since the x-coordinates are equal at their solution point and the y-coordinates are equal at that solution point. So let's take our 3/2, put it in for x. Now I think the second equation will look easier. So we're substituting back in our x in the second equation. So y plus 2 equals 4. Now our x is 3/2. So y plus 2 equals, well, 4 times 3 is 12, divided by 2 is 6. Okay, let's subtract our 2 on both sides. So we get y is equal to 4. So our y-coordinate is 4. So our solution point for this system is going to be our x-coordinate 3/2 and our y-coordinate, which is 4. Now to check your answer, you could plug our point back into each of the equations. You'll see that you get a true statement on both. So the coordinate is a solution for each equation. So the coordinate is a solution for the system. Let's take a look at these examples down at the bottom. Now what happens if we have parallel lines or the same lines? Let's see what happens. Let's take a look at example C. Our first equation is already in slope-intercept form. Our second equation isn't. So let's put our second equation into slope-intercept form. So here's our second equation, 9x minus 3y equals negative 9. All right, remember we want to get that y by itself for our slope-intercept form, so let's subtract 9x on both sides. You're left with negative 3y minus 9 equals negative 9x minus 9. All right, let's go ahead and divide through by negative 3 because we want to get that y all by itself. So y is equal to, let's see, 3x plus 3. Oh, look at that. Now our second equation is exactly the same as our first equation. So we know that they're the same line. So automatically we know we have infinitely many solutions. Now what would happen if we overlooked the fact that these equations were the same and we went ahead and did our substituting? We went ahead and put the expressions equal to each other. Let's see what would happen. All right, so say we were trying to simplify. And it looks like we've eliminated everything on both sides of the equations. Okay, that can only happen if the equations are exactly the same. So if you end up with the statement 0 equals 0, which is true, okay, this is a true statement. If you end up with this, you know that you had the same line to begin with. And if you had the same line, you know that you had infinitely many solutions. Now if you look back up a step here, we ended up on this line with 3x equals 3x. Now notice that you could have plugged in any value for x and the statement would have been true. So that can also be another hint to you that you will have infinitely many solutions. All right, let's look at the last example. So our first equation is already in slope-intercept form. Our second equation is not. Let's put that second equation into slope-intercept form. Okay, so dealing with the second equation, we're starting with 2x minus y equals negative 3. Let's put it in slope-intercept form, get that y by itself. Okay, so our second equation in slope-intercept form is y equals 2x plus 3. Now notice our slope on our second equation is 2, and our slope on our first equation is 2, so we know automatically we have parallel lines since their slopes are the same, and parallel lines have no solution. Now what if you had overlooked that fact and you kept going with the substitution anyway? Let's see what would happen. So since this y is equal to this y, we know that this expression is equal to this expression. So let's set the expressions equal to each other. So we have 2x plus 1, that's our first expression. And our second expression, 2x plus 3. Okay, let's do our simplification. We end up with 1 equals 3, which is not true. So we know we have no solution. So if you follow through with the substitution and you end up with an equation that is not a true statement, you know automatically you have no solution. So that must mean that those lines would have been parallel. All right, let's go ahead and look at some other ways to use substitution. Now these are the ways your book shows to use substitution. So let's take a look at our first example. Notice we have one of the variables already defined. They're defining y as this expression 3x. And take a look at our second equation. This equation also involves a y. We have x plus 2y equals negative 21. Okay, that's that same y. Now if y is equal to 3x, we can substitute in our 3x in place of the y since our first equation tells us that they are equal. So let's do our substitution. So we have x plus 2. Well, y is equal to 3x according to our first equation, so we'll plug in 3x for the y into our second equation equals negative 21. Let's simplify. 2 times 3x is 6x, and x plus 6x is 7x. Let's go ahead and divide through. So we find x is equal to negative 3. So our x-coordinate is -3. Now we have our x-coordinate, we need our y-coordinate. So we can plug our known value for x back into either of our equations. Remember, they'll both work since we're looking at the place where the equations share a point. We can plug it back into either to find our y-coordinate. Now you can choose which equation you'd like. So I'm going to go with the first equation because that one looks simpler. So our first equation, y equals 3 times, and our known value for x that we just found is -3. So plug in that -3 for x. All right, so y is equal to 3 times -3. Well, 3 times -3 is just -9. So we have our y-coordinate. So our solution, our ordered pair solution is -3, -9. All right, let's look at the next example. Now, in these examples, it looks like neither of the variables are defined or isolated as it was, or as they were in the first set of equations. So you have some choices to make. You could solve for the x and find out what it's equal to in the first equation and use that in the second equation, or you could solve for y in the first equation, find out what it's equal to, and substitute that in for the y in the second equation, or you could use the second equation, solve for x, find out what it's equal to, and plug it into x in the first equation, or you could even solve for y in the second equation, find out what it's equal to, and substitute that in to the first equation to find your coordinate. So I'm going to show you a couple of ways using our first equation. So we're going to use our first equation, and let's try solving for x, and then we'll try solving for y. So our first equation, let's solve for x first. All right, so let's get that x by itself. So we end up with x equals -3 minus 5y. So from this first equation, we know x equals -3 minus 5y. Now we can take our x and the expression that we found is equal to it, and we can plug it in for the x in the second equation. So let's do that. So let's use our second equation and plug it in. So 3 times, well, we know our x is equal to -3 minus 5y minus 2y equals 8. Okay, so now all we have to do is simplify. Let's distribute this 3. You end up with -9 minus 15y minus 2y equals 8. Okay, let's combine our like terms. We end up with -17y equals, okay, add your 9 on both sides. You end up with -17y equals 17. So let's divide through by -17 to get our y-coordinate. So we know our y-coordinate is -1. So since we know our y-coordinate, now we can take our y-coordinate and plug it back into either of our equations to find our x-coordinate. So let's do that. The first equation looks simpler to me, so I'm going to use that first equation. So putting our y-coordinate into our first equation. So we're subbing in the y into the first equation. So in our first equation, x plus 5 times, well, y is just -1 is equal to -3. So x plus -5 equals -3. Let's add 5 on both sides. X is equal to 2. So our x-coordinate is 2, our y-coordinate is -1. We know that our solution point must be 2, -1. All right, now what would have happened if we had solved for y in the first equation instead? We should end up with the same answer because the solution will be the same since we're dealing with the same lines here. Well, same lines as in the first example here. Okay, so let's take our first equation. X plus 5y equals -3, and we're going to go ahead and solve for y this time. So let's subtract x on both sides. You get 5y equals -3 minus x. Divide through by 5. Y is equal to, well, let's see, -3/5 minus 1/5 x. And we can rewrite it as -1/5 x minus 3/5. All right, so now we know In our first equation, y is equal to negative 1/5 x minus 3/5. So if our y is equal to this expression, we can put this expression in for the y in our second equation. So let's go ahead and do that. Let's substitute in what we know for y into our second equation. So in our second equation, we have 3x minus 2 times y, but we're substituting in the expression we found for y. All right, so let's go ahead and simplify. Well, negative 2 needs to distribute, so we have 3x. Negative 2 times negative 1/5 is positive 2/5 x. Negative 2 times negative 3/5 is just 6/5. All right, so let's go ahead and combine our like terms. We have 3 and 2/5 x plus 6/5 equals 8. All right, well, let's put this into an improper fraction because that's a little easier to deal with as we're simplifying things. So that would be 17/5 x plus 6/5 equals 8. Let's subtract our 6/5 on both sides. We end up with 17/5 x equals, well, 8 is the same as, let's do a little side work, that's 40/5. So 40/5 minus 6/5 gives us 34/5. Now to get that x by itself, we need to multiply by the reciprocal since we're dealing with a fraction. We end up with x is equal to, well, 34/5 times 5/17 ends up being 2. So we know our x-coordinate is going to be 2. Now let's take our x-coordinate that we know. We can plug it back into either of our equations to find the y-coordinate. I think the first equation looks simpler, so we're going to sub in our x into the first equation. So our first equation, our x is 2 plus 5y equals negative 3. Okay, let's go ahead and start our simplification. So subtract 2 on both sides. We end up with 5y equals negative 5 divided by 5. Y is equal to negative 1. So our y is negative 1. Our x-coordinate is 2. So our solution is 2, negative 1. And that's exactly the same solution we found when we did it the first way. So you can either solve for x or you can solve for y. You can do it in the first equation or the second equation. As long as all your moves in algebra are legal, you'll be good to go and you'll be able to find that solution point. So always go with whatever looks the simplest to you. All right, last set of examples. So what happens if we have parallel or the same lines? All right, let's go ahead and try out example C. So notice one of our variables is already defined for us. We know y is equal to 3x plus 2. Let's go ahead and substitute in for the first equation what our y is equal to, since that will be the simplest as our y is the variable that's already defined. So in our first equation we have 6x minus 2. From our second equation we know y is equal to 3x plus 2. Okay, simplify. Let's distribute our negative 2. All right, so I see like terms. 6x and negative 6x is 0, so we're left with negative 4 equals negative 4. And that is a true statement. So were these lines parallel or were they the same line? Well, let's take a look and see about our equations here. Now our second equation is already in slope-intercept form. Our first equation is not. Let's take our first equation and put it in slope-intercept form. We'll be able to compare the slopes that way. So we're starting with 6x minus 2y equals negative 4. Let's get that y by itself. You end up with 3x plus 2. And look at that. So our first equation is exactly the same as our second equation. So we know that these were the same line. So we know that we have infinitely many solutions. So if you end up with a true statement here, you know that they must have been the same line and they will have infinitely many solutions. All right, so what happens if the lines are parallel? Well, we can't tell exactly from here if those lines are parallel, so let's go ahead and just do the substitution and we'll see what happens. So our y in the second equation is already defined for us. We know that this expression, 3x minus 4, is equal to y. So let's substitute that in the first equation for our y. So from our first equation, negative 3x plus, well, our y is equal to 3x minus 4. We can substitute that in. Let's simplify. Well, I see like terms, negative 3x plus 3x is 0, so you end up with negative 4 equals 1. Now that is not a true statement. So let's see about these two equations, see whether they were possibly parallel or a different case. So the second equation is already in slope-intercept form. The first equation isn't. So let's go ahead and put our first equation into slope-intercept form. So we're starting with negative 3x plus y equals 1. Let's get that y by itself. Add 3x to both sides. You end up with y equals 3x plus 1. So our first equation, the slope is 3, and our second equation, the slope is also 3, but notice they're not the same line. But they have the same slope, so that means they were parallel, which means they have no solution. So whenever you end up with a statement that is not true, you will know that the lines were parallel, so therefore there is no solution.